So we're going to start our session now. So this is Hala Ali. She is a PhD student from CS Virginia Commonwealth University, and she's going to talk to us about post-incident runtime SBOM generation. Take it away.
Introduction. Hello, everyone. I'm Hala Ali, and I'm here to talk about post-incident runtime SBOM generation from Python memory. So I know the title sounds a bit intense, but the question behind it is pretty simple. The question after a Python application has been compromised, can we still figure out what packages were loaded and running? I don't mean here what was in requirement.txt. I don't mean here what pip freeze tells you, because the file system might not tell you the full story, right? And what was installed, it's not always what was running. So especially in Python, it's dynamic language, and the imports can be dynamic, loaded at runtime. So I mean here what was exactly in a Python process when it was running. And that's the question this talk tries to answer. So before I go further, I'll just quickly introduce myself. So I'm a PhD candidate in computer science at Virginia Commonwealth University, and my research focused on memory forensics, software supply chain security, and malware analysis. I work on this project with Andrew Case. He's a director of research at Velocity, and he's a senior incident responder and malware analyst. Unfortunately, he couldn't make it to PyCon. He's presenting at a different conference, so today you got me. So, all right. So, why this topic is really important for Python? Well, we know Python application depend heavily on third-party packages, and PyPI is a place where a lot of us trust every day, and attackers know that too. Just in 2025 alone, more than 2,000 malware reports were processed by PyPI. And these are not just tiny packages. We are talking on Clyde LLM, a package with more than 100K downloads in just 2.5 hours. We're talking about elementary data, a package that has more than 1 million downloads. A malicious version of it was uploaded to PyPI just last month. And the most recent one, Mistral AI, just a few days ago, it targeted LLM developer, and the attacks or the malware is triggered at runtime. So when you import the package, there's a function is called, and that function tries to launch and download malicious payload remotely to your machine. So these attacks are not theoretical. They can reach our environment, our system, our production environment. So if that happens, the question becomes, how can we know what was running on our system? If our application really used these malicious packages or not, right? So, and SBOMs try to answer this question. So a quick level set, if you haven't worked with SBOM before, SBOM is just ingredient list of your software. It tells you the component of your software, their version, what third packages you use in your application, and how they rely on each other. So why people care about SBOM? Because they want to know what's inside your application and how these components rely on each other. And they really want to know what they need to fix if a vulnerability just shows up. So it sounds pretty simple, but there is an important catch. SBOM depends on when you look. There's build SBOM, tell you exactly the packages or the component you use when you build or pack your code. And the deployed SBOM tell you what you install in your environment. But runtime SBOM or dynamic SBOM tell you the actual component used by your application, the exact versions used by your application. So why this talk focus on runtime SBOM? Because the majority of SBOM, existing SBOM tools, They're useful, but they give you just a static view. They estimate the version that might be installed on your system, not the actual version. We've seen so many tools, they really just, I would say, report the metadata or just like parse the configuration file of your Python project and just tell you like some version could be pen version, like, there's so many like setup.py requirement.txt. So they just estimate the version that may be installed on your system. And different tools, different SBOMs for the same application. They parse the configuration files in different way. And Python even make it harder. Python, all of us, we know like it's dynamic language, flexible. It's really good for developer, but it's nightmare from security perspective. So like what installed or what already in your like configuration file, you don't necessarily to install all the exact version. It depends on your system and your environment. And your application doesn't necessarily to use all the package and install it for it, right? So, and the file system may not tell you always the full story. And I can give you a real scenario. Imagine you have two services running in your environment, Django and Celery. Both services, they use like asgref. It's like a third or dependency used by both services. Those applications running in your production, you can't just like reboot them or just like stop those applications. So now asgref gets updated. Django has like set reloader. It detects the update and the new version and upload it in memory. Now Celery doesn't have this feature. It just keeps using the same version, like startup version. How can we trust file system? Well, you might say, okay, like we have Runtime SBOM tool. There are so many commercial SBOM tools. Well, this tool, they really work on debugging, on instrumenting the interpreter itself. They really need access to Python process. They really need to debug the Python process. But in production system, when incidents respond happen, we cannot, like, systems cannot be debugged, cannot instrument the debugger, the interpreter. We cannot even debug the system. We just have malware incident. What we can do? How can we still generate SBOM? Well, we can still generate SBOM from memory, right? It tells you the truth. So, and this talk about how we can generate runtime SBOM from memory. So, all of us, we know when you import module in Python, the interpreter, like, it has so many like internal component, finder, loader, try to find the module on your file system and create like call loader and try to create module object and cache insisted module, like the interpreter cache or registry for those modules. So I said like we need to generate runtime SBOM from memory. How? We really need memory forensic. Memory forensics is the process of capturing and analyzing the memory or the RAM of your system. When you have binary files, how can we still parse those files and generate runtime SBOM? In memory forensic, reflect the runtime state of your system. And we know, like an operating system, we have the kernel level, we have the user land level. At the kernel level, there's like one of the most popular memory forensic tool work at the kernel level, it's volatility 3. So it parses the data structure of the operating system. And it gives you exactly the data structure or what's running or what's inside your operating system from memory. This tool helps us to identify the Python process. So, to really understand what's inside a Python process, we created a new tool, a new memory forensic tool, built on volatility to help us parse the Python process from memory and really understand what's inside the Python process. So in memory, like if we have just the binary files, we have the memory dump of your system. We know like Python application or Python process is just executable file, right? So first, we know like there are so many global symbols in Python. They represent the entry point of your Python application. So we had first to parse the header of this executable file, then identify the runtime or the entry of the Python runtime. It's like py, the runtime symbol, global symbol. And from there, we could access the interpreter, the main one, the interpreter data structure, and then we could access all the threads of Python process and the garbage collector. And from the garbage collector and the threads, from the threads, we could access all the stacks, and we could recover all the functions from the stack, and we could recover all the function called chain. And from the garbage collector, we know it has like 3 generations, right, of objects. So we parse all the double linked list and recover the objects from the garbage collector. So we extracted so many objects, modules, dictionaries, function. And as I said, SBOM tell you the packages of used by your application. And packages are set of modules, right? So we focus on modules to recover SBOM from memory. So in memory, when there's any like module created, or when the Python creates any module, so it's represented in memory as PyModule object in memory. So it has like features. It has name, it has package, it has version, which is optional. There is no guarantee to have version in memory. It has file, it has the loader objects like reference or point to loader object, and it has the module specification in memory. Well, is it just easy? We parse data structure and generate runtime SBOM? Of course, no. It's really challenging. We spent 2 years just like to recover SBOM from memory. So why? Because as I said, like Python, it's dynamic language, flexible language. It's really good for a developer. But like we could like generate, like create malicious module and just delete them. We could like even overwrite modules in memory. And like we know the interpreter has like built-in modules, right? And we have like standard library modules, and we have the application modules, we have third-party modules. All of them, they coexist in the same process memory. And also, as I said, the version information, it's optional. There is no guarantee to have version information in memory. It's also another challenge for us. And because SBOM is a list of packages, and the packages, it's like represented as a set of modules in memory. So there's no one block in memory to tell you, okay, this is a package X, this package Y, this package Z. No, we don't have that in memory. We have just modules. So we came with this novel memory forensic tool that try, after like identify the entry runtime, the entry point of the runtime, the Python runtime, it go through all the module, it try to recover all the module from all the process. Well, like there's so many Python applications, they are really complicated applications. They don't just have one process. Like Apache Airflow, it has more than like 26 processes running at the same time. So we had to parse all the memory of each process and generate, create, or get the module from all of them. And after that, we have to filter out the built-in, the standard library modules, and just try to focus on the application and third-party modules. And after that, even we group them under their parent package, like following the BEP 427 and 451. And as I said, the version, it's optional in memory. It's really like challenging to recover version from memory. That's why we figure out like Python itself, the interpreter itself, it caches some metadata here. It caches some metadata in memory. So it just gives you the package name and the version. So we used regular expression to extract the package name, just the installed package the name of the installed packages and their version. And we know like the install name is different from the runtime name. So we had to normalize the install name, and then we had to query PyPI using the install name just to get back from PyPI the runtime name. Then we can just matching between the install name and runtime name and just assign the version of the runtime module or packages in memory. That's how we fix the version problem. After that, we use like CycloneDX to standard to write SBOM at a JSON file, and then before that, then like SBOM is not just, as I said, it give you the packages and their version and how they rely on each other, right? So how can we identify the relationship or the transitive relationships between the modules? So we had even like to parse the bytecode of the function. We went through each module and we parse the bytecode from memory. After parsing the bytecode of each function, we could like identify the relationships between all the modules and how they rely on each other. So SBOM alone, it's useful when we use it, right? And like to use SBOM, we use like vulnerability detection tools. There's like tools like from Anchor, there's Gripe, right? So it takes SBOM as input, and also it gives you like the vulnerability or the vulnerable CVEs of your applications. Is that enough? Is that enough if you know there is a malicious package in your system means the entire application is vulnerable? Of course, no. Why? Because if you just like query NVD or GitHub and get the vulnerable function, then what? Then we need to identify the impacted module in memory. So here there is an example. If you have like multiple modules in memory, we can see like E is a vulnerable module, okay? And we can see here there is two functions are vulnerable. We've seen here there is a call path from C to E, right? But for other module, there is no call, right? So why do I need to replace all those modules? I can just focus on C, I can just focus on D, right? And update them. No need to update the entire application, right? So, I said, again, I repeat, Python, I love Python. It's really like flexible, dynamic. But recently, I figured out we can manipulate the interpreter itself. We can inject malicious module. We can abuse the flexibility of Python. How? We could create malicious module and just delete it from the code, right? We could create benign module and just assign malicious, like just the malicious payload assigned under like benign name. We could even redirect the imports of the finder, redirect the finder to malicious loader in the Python, in the interpreter itself, and try to just call malicious module. We could do that. And not only that, the garbage collector itself, we could use the C type to manipulate the double linked list of the garbage collector and try to unlink object from there. That's why I said if we go back here, I said multi-layer. Multi-layer. What do I mean by that? Because of this challenging, I had to scan the interpreter registry. I had to scan the namespace of the active function from the threads of the interpreter. I had to scan all the interpreters. There is not only one interpreter in your Python process. There is also sub-interpreter. So we had to scan all of them. Was it enough? No, it depends on your object. It depends on your purpose. How deeper you want to go. We scanned the garbage collector. Even we went deeper and we scanned the arena pools. And we could recover the small size objects. And not only that, we scanned even the heap, the entire heap arenas, structured way to recover all the modules. Then we will get so many duplicated modules, of course, but we could recover the entire set of module. And the module still be in memory until the reference count greater than the 0, it get pointed by other objects in memory. So for evaluation, So we came with MEM SBOM. It's a new novel like memory forensic tool, so we had to evaluate it to see if it's really useful in real environment in production for companies. So we tested on real, like 51 real application, Python applications from different categories. We evaluated against like web frameworks, ML platforms, task schedulers, and 19 more categories. We compare with 8 existing SBOM tools like SIFT, Trivy, CDXGen, CycloneDX, Python, SBOM for Python, ORTJEC, and PEP SBOM. And to evaluate it, because it's runtime SBOM, we had to come with 2 different kind of ground truth. The pip freeze give you the actual installed packages on your system, and we use the site customize, like the module we could like just place in the site package of the environment, and to just kind of instrumentation to recover all the runtime module. So we've seen like when we tested the existing SBOM tools, we've seen like they really don't support, they're really useful from static point. But there is no one tool can support all the configuration files of your Python applications. We've seen like SIFT, like it just like it doesn't like support the pipe project to TML. Like under the BEP 621, and Trivy, it has like limited support of the configuration file. We've seen SBOM for Python, it's a new one, but also it has like limited support of setup.py. Like they used, like to be honest, for setup.py, they use regular expression. So if you just change one character or change one location or one entry, so this tool cannot parse the setup.py. Even the requirement.txt, we know like requirement.txt, it doesn't always have like pen version or specific version, right? It could be like greater than 5.2, less than, it depends. Then the actual version, it will be depends on your system, depend on your environment, depend on your operating system. Right? So we've seen like the other tool, like because like static, they rely on the metadata, the configuration files. We've seen them, like there is a recent like research tool, it's PEP SBOM, try to rely on the package manager, but they use like different, I would say version resolution algorithms. That's why even though it's still like cover most of those files or configuration files, it still has kind of limitation in terms of version accuracy. Okay, let me drink some water. Sorry. Okay. So as I said, like the average success rate of this tool, like if you really want to use this tool, they are useful, but as I said, they are static tools, not runtime SBOM tools. So some of these tools, they work in a real environment, they work in deployment mode, but they just can scan, like just to scan the installed, they rely on file system. Even if they work in deployment mode, they work on the file system. And as I show you in the real scenario, the file system may not always tell you the full story. So we've seen they have like not 100% coverage of all the packages installed on your system, even if you use them in deployment mode. And when it comes to the version accuracy, SIFT is good because when you use it in deployment mode, it just scans the installed version. So compared to MEM SBOM, it gives really good results. But other tool, PEP SBOM, for example, it tried to simulate and estimate the version that might be installed on your system, not the actual one. So we've seen limitation in terms, as I said, in version accuracy. Not only that, Python, as I said, is a flexible language, so there's so many applications. This application are plugin application, right? They can like just import modules at runtime. They can just like try to, even without, you don't need even to install package. You just use the folder of that package, download it on your system, and you can just use the module from that package. Even no need to install. That's why we found so many tools between like 4 and 6%. they missed like this runtime modules. They don't really cover all the runtime module when they import it at runtime. So, and the most interesting thing. So, what we found like out of 51 applications, our evaluation set, we found like 5 applications. The installed version is completely different from the version we found in memory. How that happened? When any developer tried like to update their version, that they maybe, I don't know, like they maybe forgot to update or change the version or the version feature in their code. So on memory, the code is reflected in memory, right? So when you install a new version on your system, okay, it shows the new version, but in memory, we found like different version. So this version, like in memory, it's just reflects what represent in your code, in the developer code. So also that helped us to find the inconsistency between the tools. So as I said, why SBOM is useful? SBOM is useful when it's used to find like vulnerabilities, right? So, but I can give you here just a case study, a real one. Like we know like Tornado, this version 6.4.2 is a malicious version. So it has like CVE, this version, specific version, it has CVE, deny of service, and it has just like in this particular function, so it keeps just like with any malformed input, so it keeps parsing the input, so the attackers try to exploit that to generate like a large number of logs and try to cause deny of service through this version. So we found like 6 applications in our evaluation set that use this malicious version, and some of them, the recent version, they're still using this malicious one. Well, can we just tell, okay, if your application use like Tornado version 6.4.2 means your application is vulnerable? No. So it doesn't like mean you just, when you import a malicious version, it means you really used in your application. We found like Jupyter Lab and Streamlit, they use this malicious version of it, but only the Streamlit use the vulnerable function. So instead of updating like 6 applications, you just need to focus on Streamlit and just update the vulnerable part of it. No need even to update the entire application. So here I can give you an example. One of this application, it's a Spider. Spider, it has like transitive like call of the benign module from like Tornado. It's IO loop, so just benign, so no need to update this function. On the other side, we've seen here Streamlit, it has like internal call of the malicious parse body argument in that CVE that's caused the deny of service. So it's malicious, so we need to focus on this part. And that's how we showed like how like runtime SBOM from memory, it's useful to reduce the false positive. So in memory, how that happened, like if we see like there are so many like data structure, as I said, we just see like modules in memory. So they're connecting to each other. There is so many calls from the Streamlit, it called web, from web server, from server update like file request handler, up to getting the malicious function or the function that called the malicious one from Tornado. So it put, when we analyze the bytecode of like this function, we saw like there is call of the malicious function from that CVE. So to wrap up, there's 3 main points I really want you to take away. So we've seen like SBOM tools, they are really useful from static point. And we've seen like they rely just metadata, even if they work in deployment mode, they still rely on the file system, and the file system may not always tell you the full story. We need runtime SBOM. And Python make it harder because it's dynamic, flexible language. So what you just have in your configuration file, it doesn't mean you install all of them or you install the exact version. And what you really like install, it doesn't, like your application doesn't necessarily to load and use all the packages you installed on on in your environment. And that's why, especially in incident response, when really like the supply chain attackers access our environment, when the accident just occurred, what we can do, how can we know what happened, right? So that's why we really need memory SBOM. That's why we came with MEM SBOM, our memory forensic tool, to provide, to help the community to recover runtime SBOM and try to figure out exactly what happened in your environment. So thank you so much. Please, if you have any question, you can feel free to ask or come find me after this talk. And my email on the slide, Andrew as well. And thank you so much.
Thank you very much. A very interesting talk. It seems to be very involved. A question about Python versions. What Python versions are supported? And do you foresee future work like Python 3.15, 16 come out if they change all this import kind of procedure? What versions are supported?
Sorry, I didn't hear you. Sorry.
What Python versions are supported? Because this seems to be very involved. You rely a lot of the internal structure of Python, and the Python import system might change over time. So do you have any limitations of Python versions? And do you foresee major changes with future Python versions potentially?
Right. So thank you. It's really excellent question. So our tools support up to Python version 3.14 and 15. So we know the garbage collector, especially in the recent versions change, we have the older and the generation change the data structure. So we built this tool to consider all the version up to 3.14, and it will be open source soon. So so we consider all the data structure changes.
Great talk and excellent tool. When you make it open source, do you worry?
Oh, yeah. So this tool recently got accepted at Black Hat Arsenal. So it will be open source by just 2 months. So it will be open source, to the community.
Are you worried that then the malicious actors will try to use the description of your tool and the way that it goes looking for things to try and hide
right.
in other...
We are now what we're trying to do. It's our ongoing project. So we're trying to come with solution first, then we try to hack our solution. So we try just we came with solution, right? Then we think, okay, well, we came with MEM SBOM, so how can we trust memory, right? So we figure out there's so many ways to play around, change data structure in memory. So that's why we're trying to come with solution. That's why I came with multiple layers to recover module from multiple layers. So we'll try up to, it's kind of game theory between hackers. And so we're trying up to who's gonna win the game, hackers or memory forensics. So. Thank you, good question. Yeah.
All right, everyone. I think that's all the time for questions. Thank you so much. Another round of applause.
Thank you so much.